So in this video I want to introduce you to some of the underlying concepts of sample means hypothesis testing. So really, where does it come from? How does it work? Now I'm going to be using this website and another in a moment, but I'm going to be using this website first. This is from the University of British Columbia. The link to it is in the description below, and if any teachers are watching this, I do strongly recommend that you have a play around with this, because I think it's a really good way of visualizing what's going on. So, how does it work? Well, the concept is this. Let's say that you've got this huge lake that is full of fish. Not literally full, obviously. So you've got this large lake that's teeming with fish, and of a certain population of fish, and you're interested in their lengths. So how long they are on average and their spread, so their standard deviation. Now, you can't just go in and catch all of the fish and then measure all the lengths. That's practically impossible. So we can't do that. So what you would do is you would take samples. So you might decide to take samples of size 5 or 10 or 20. So you catch up 5 at random, or 10 at random, or 20 at random, and then you could measure their lengths. Now, in order to do this, I've been able to, take away the issue of actually catching the fish for myself. Thankfully, this website is going to do it for me. And essentially, what it does is I can catch a fish, it measures its length, so in this case 119 millimeters, and it plots it on the graph. Okay, so I could take another fish, 87 millimeters that time. So it's randomly selecting from a population distribution of mean 106 with a standard deviation of 30. Okay, and it's waiting for me to make a sample of 10. So currently I've just got 2. So let's catch another fish. That one's 90, so that's going to pop that there. And this one's 137, a little bit larger. That pops it there. And I can keep selecting my fish until I've got a sample of 10. Okay? So, what happens next? Well, what we're going to do is we're then going to calculate the mean of my sample. So, I'm going to add up all those lengths and then divide by 10. Okay, and it's going to plot it on the graph below. So, what we're going to do is we're going to do this loads and loads and loads of times. Now, if we take one step back before we do that, let's just think about the situation. We've got this large lake, we've got all these fish in it, all these fish in the lake, sorry, and we don't know their mean and their standard deviation. Okay, if you were doing this in practicality, you wouldn't know. So what you would do is you would do this process in order to be able to estimate that. With the problems that we deal with in sample means hypothesis testing for A-level maths, we only deal with scenarios where we know the population mean and the population standard deviation. Okay, so that's why I know that the population mean is 106, and I know that the population standard deviation is 30. Okay, so I'm given that information from the outset. These are not values that I have to estimate. That would mean that we would have to go down a t-test route, which we don't on this course. Okay, so just to kind of put that out there. So we'll always have that information within the question. So let's take another sample of 10, shall we? So let's take another sample of 10 fish. Okay, different sample this time, and we calculate the mean, and it plots it on the graph below. Right, let's do a complete sample of 10. Okay, it does it in one go for me. There's my sample, calculate the mean. Okay, and what we're going to do is we're just going to keep doing this. Okay, take a sample of 10 fish, calculate the mean length, plot it. Take another sample of 10, calculate the mean, and plot it. Okay, and we're going to keep on doing this. Now, in order to speed this process up, let's just put in a load more, and a load more, and a load more, and a load more, and a load more. Okay, in fact, let's put in loads and loads and loads and loads and loads. Okay, now what I'm going to do is I'm going to put in this curve here. Now this is the normal distribution curve that is the population. So this has a mean of 106. You probably just about see it there. So it's 106 mean with a standard deviation of 30. Okay. Now compare that distribution with the distribution that we're getting for the sample means. So I can actually overlay the sample means distribution as well. Now what do you notice about those two graphs? Now one thing might be that one is taller than the other. Now that is true, that is the case. I'm not particularly fond of having frequency up the vertical column, so yes, it will be taller than the original normal distribution if you plotted the normal distribution, but for the reason that it is thinner. Okay, now notice how both of these distributions have the same mean. They are centered both around 106. Okay, so the mean of the sample means is 106, as you would probably expect. But the key difference is that it's thinner. Okay, so why is it thinner? That is the next question. Why would the means of the samples be more consistent than the original data? Okay, now why would that be the case? Well, the reason for that is because as you are taking samples of size 10, what's happening is that sometimes you will catch a large fish in that sample. Okay, so if we take a sample again of 10 fish, okay, now notice how I got this larger fish here, okay, and which in the grand scheme of things, you know, is unlikely, but possible, but unlikely. And I got these two smaller fish here, okay, which again, unlikely, but possible. But the thing is that because you're taking a sample of 10 and you're adding up all those lengths and dividing it by 10, those outliers are having less of an impact on the overall mean of the sample. So the larger the sample size is, the less those outliers will make an impact because their lengths are getting averaged out. Okay, so if I took, let's say if I changed this, so let's refresh, and I'm going to change the sample size this time to, let's say 30. So each sample I now take has 30 fish in it. Okay, so here's my catching my sample of 30 fish. And I calculate the mean. Now let's do that again. Calculate the mean. Again. Calculate the mean. Okay, and let's just keep doing that. So here's the population. Here is the distribution. Now, The way that it's drawn at this time, actually, it looks like the original population curve is about the same height, if not higher, than the sample means. Now, if you put those two graphs side by side, because one is thinner, they both, remember, have to have an area of 1, so actually the thinner one will be taller, okay, if you drew them on the same axes, right? So, don't worry about the relative heights of these, but notice how my sample means distribution, the one at the bottom, is much thinner. It's thinner than it was last time. So the larger the sample size, the thinner it is. So the question is, can we predict how thin the sample means distribution will be based on the standard, or not the standard deviation, based on the sample size rather? Okay, so because n was 30 in this case, could I tell how thin it was going to be? So for that, I'm going to use another website, and again, this is linked in the description below. Now this one is a lot more old school, okay, but I've used it for years. It's still really, really good at developing this idea. So this is from onlinestatbook.com. Really, really good website. So, as I said, it does look a bit old school. I'll just make it a little bit bigger, okay, but it does exactly what I want it to do. So what you're seeing is, on the top graph is the parent population. So this is the population of all those fish in the lake. Now the one that we have set up is a normal distribution with a mean of 16 and a standard deviation of 5. Don't worry about kurtosis. I do get some questions about, you know, what does that mean. Feel free to look it up. But you don't need it for the A-level maths course, so I won't delve into that. So what I want it to do is it's going to sample the data, and this one is going to take samples of size 5. Okay, so it's going to take a sample of size 5 and then plot the mean. It's doing exactly what the previous website was doing. Okay, really, really useful to visualize it. Let's do 5. Right, so I'm going up in 5, so this is samples of 5 that I keep adding on here. It's a bit slow in it. Let's do it, add on 10,000 samples. So it really kind of like jumps up. We could do a few 100,000 if we wanted to. Okay, so what are we seeing here? We're seeing a normal distribution. On the left-hand side, it tells us, so this is what the other website doesn't do, unfortunately. It tells us the mean of the samples that we've got, so 16, which matches the mean of the population. Great. But the standard deviation is 2.24. So the question is, where does 2.24 come from? So what we're going to do is we're going to have another graph going. So this one, I'm going to do a mean of, let's go with 10. Okay, so the first one is going to take 5 and then plot it. The second one is going to take 10 and then plot it. Okay, so let's get 5 each. Let's go up in 5s. So each time the top graph is taking samples of size 5 and plotting the mean, and the bottom graph is taking samples of size 10 and plotting the mean. Right, let's do it a few thousand times, shall we? Let's add on a few 100,000s. Okay, so let's see, what do we notice? Well, the two graphs have the same mean. One is 16. The top one is 16, the bottom one is 16. Standard deviation of the top one is 2.24, the bottom one is 1.58. So, how am I getting that value? 2.24, 1.58. Okay, well, let's do one more, shall we? Okay, so we've had 2.24, 1.58. That's coming from n is 5 and n is 10. I'm going to do n is, let's go with n is 20 and n is 25. Okay, so you might want to jot these numbers down and see if you can work out what the link is. How do you get that standard deviation for the samples from the standard deviation of the original, which is 5, and the sample size? So this one is 1.12, has a standard deviation of 1.12. This one with n is 25 has got us a standard deviation of 1. Now, that definitely helps, doesn't it? Standard deviation of 1. So how are you getting that? Well, if you haven't spotted it, then the way that you get your standard deviation of the sample means, which is known as the standard error, so rather than standard deviation, we call it the standard error, we get the standard deviation of the population, which is 5, and divide that by the square root of the sample size. So here, this is 5 divided by the square root of 25. That's how you get 1. This 1.12 is coming from 5 divided by the square root of 20. So when we had n is 5, and we had that 2.24, this is coming from 5 divided by the square root of 5. Okay, and that is your standard error. And so what that is telling you is it allows you to model the scenario using the distribution of the sample means. Okay, so you might be going, well, okay, where does the hypothesis test come into this then? Okay, well, in order to explain that, we're going to go back to the fish scenario, okay, just so we can kind of visualize it. So how does this work? Well, the idea would be that you would have a population, which in this case has a mean of 106 and a standard deviation of 30, and you're going to take a sample of size 30. So let's say you go out onto the lake and you catch a sample of 30 fish. You measure each of them, you put them back into the lake, and of your 30 measurements, you then divide that by 30, and you get your sample mean. Now, what we then need to do is determine, is the mean of your sample extreme enough to suggest that the population standard deviation that we know, and the mean standard deviation, is that right or not? Sorry, I should just say the population mean. Is that correct? Because we're not going to test the standard deviation, sorry. We're going to test the population mean. So, does that sample of size 30 that I've collected suggest that the population mean is actually greater than 106, or less than 106, or different to 106? Okay, so it's all about, you've collected this sample, and the sample mean there is that large enough or small enough to reject the null hypothesis. Okay, so that's the consideration. That's the test. That's the idea. Okay, so this hopefully has displayed to you kind of what the idea is, where all these kind of concepts are coming from, and now we're going to do the mathsy bit. So notation wise, what we're looking at is a population, so this is our population of fish in the lake, which is normally distributed with a mean mu, which we are told in the question, and a variance sigma squared. So you might get told either the standard deviation or the variance in the question, but you will get told it, okay, one or the other. And then we have the sample that we collect. So the samples, which we denote with x bar for sample mean, okay, so we regularly use x bar for sample mean, don't we? Okay, so understand that to be the mean. So x bar is the distribution of sample means, which is also normally distributed, and they have the same mu. Now we saw that because when you compare the two distributions side by side, here is your population, so here is x, okay, and then the sample means centered at the same value but will be taller and thinner, okay, so they have the same mean, so these are your x bars, okay, but the variance is clearly different. The variance has to be different because it is thinner and consequently taller, because they both have to have the same error of 1. And as we worked out, as we showed through our graphs, that this is sigma squared over n. Now, when we were looking at it, we were saying, well, it's the standard deviation of the population divided by the square root of the sample size. So the standard deviation of the population divided by the square root of the sample size. Okay, and this is what we refer to as the standard error. So it has a special name. Okay, essentially it is the standard deviation of the sample means. So this is its standard deviation, whereas its variance, so this, is the standard error squared, because remember we always put the variance in here where we write out the normal distribution. So this is sigma squared over square root of n squared, which is n. Okay, so this is the variance of the sample distribution, the sample means, and this is the standard deviation, or standard error, of the sample means. Okay, so that is notationally and diagrammatically what it looks like. And so this is where this stuff comes from.